Good morning. In the last class we had discussed about superposition and interference, which are the properties of electromagnetic waves. Waves also exhibit another property which is known as diffraction. What is diffraction? Diffraction is the phenomenon of bending of waves. Here in this class we are going to study more about X-ray diffraction. So how can we observe diffraction of light? Diffraction of light can be observed using a device called diffraction grating. Diffraction grating is also known as diffraction transmission grating or diffraction reflection grating. Here you can see in the picture, this is the picture of a diffraction grating where you can see a glass plate which is high quality glass plate, and this glass plate contains large number of fine lines which is cut using an instrument. So here you can see that 15,000 lines per inch. That means this grating contains 15,000 lines per inch. So grating is basically a glass plate with a large number of lines cut on it. So what happens? The space between the lines is transparent and the lines act as opaque regions. See, we are cutting the glass plate with the lines. So these lines will not allow light to fall through it. But the spacing between the lines is transparent and it will let the light to pass through it. So that the space between each lines will act as a slit. So the grating is like a large number of slits, each slit being the space between the lines. So the diffraction grating consists of many equally spaced parallel slits. This slits is formed by cutting the glass plate with the lines. And a typical grating contains several thousands lines per centimeter. Here you can see 15,000 lines per centimeter in this grating. So this grating consists of large number of slits which helps in the diffraction of light. And due to the combined process of diffraction and interference, we can see the pattern on the screen. And the intensity of the pattern on the screen is the result of the combined effects of interference and diffraction. See, here you can see a diffraction grating. So these are the lines drawn, isn't it? So they will not allow light to pass through this. But the spacing between the lines act as the slits. So here you can see 1, 2, 3, 4, 5 slits you can see, and there are 6 lines are drawn, so that there are 5 gaps between them. So these 5 gaps act as slits. So this is the diffraction grating which we are using to observe the diffraction of light. So the incoming plane wave of light is incident on this diffraction grating. And here you can see the light is diffracted. If the light is not having the property of diffraction, what will happen? This incoming light wave, when comes to the slit, it will only hit at this point, isn't it? But here you can see there is a diffraction happened, and due to this diffraction you are getting and diffraction and also interference. See, at this point P, you can see the light coming from this slit, this slit, this slit, this and through the slit. So all the light waves gets incident on P. So the superposition of waves causes interference there, and due to the interference on the screen you can see several intensities, that is maximum intensity at the central point of the screen and minimum intensity which is known as the first order maximum on both sides. So using this diffraction grating we can analyze the diffraction of light, and by the combined process of interference and diffraction we can see the maximum intensity on the screen. Now let's see what is an angle theta here. See, the light get diffracted from the consecutive two slits. So the angle between that diffracted light is given as theta, and the spacing between the slits is given as d. So what is the sine theta? Delta by d, or delta is equal to d sine theta. And in the last class we had already studied about constructive interference and destructive interference. Now what is the condition to get a constructive interference? That is maximum intensity at the screen. That is given by d sine theta is equal to m lambda, where lambda is the wavelength of the light used and m is an any integer that gives you the order of the diffraction pattern. See, the maximum is obtained at the central portion. So this is the central or 0th order maximum, and the intensity decreases as we go away from this central maximum. So this is the first order maximum having lower intensity than central maximum, and after first order you can see the second order, third order, etc. So the order of the pattern is given by an integer that is small m. So for central maximum we are substituting m as 0. For first order we are substituting as 1, and for second order it is 2. Now what is theta? Theta we had already discussed as the angle between the diffracted light rays. And d, what is the d? What is d? D is the distance between slits. So d is the distance between slits, m is the order of the maximum. So this is the condition for getting the maximum intensity on the screen, or condition for constructive interference. If the incident radiation contains several wavelengths, each wavelength deviates through a specific angle. Here we had discussed about a single wavelength, a monochromatic wave, so that we can substitute lambda as its wavelength. But if the incident radiation contains several wavelengths, each wavelength will deviate according to its own angle. So we had discussed the diffraction grating as a device which helps you to observe the diffraction of light. And the main advantage of this diffraction grating is its superior resolution. What is meant by resolution? Resolution means it enables to get a very good separation of lines that are close to one another. So this diffraction grating is a very useful device for measuring wavelength. Now we can move on to our topic XRD, that means X-ray diffraction. What is meant by X-ray diffraction? By the word itself, diffraction of X-rays. Can we use diffraction grating for X-ray diffraction? No. Why? Because if we want to study diffraction of lower wavelength radiation like X-rays, we cannot use diffraction grating. Because X-rays have only lower wavelength, that is approximately 0.1 nanometer. So we should have a grating whose slits were less than 1 nanometer apart. That means for diffraction to occur, the slit width should be approximately of the same order of the wavelength of the light used. We are using a light, isn't it? And that light is having a particular wavelength. And we are using a diffraction grating having a particular slit width d. So that for diffraction to occur, the slit width should be approximately of the same order of the wavelength of the light used. And here, if we are studying about X-ray diffraction, the X-ray wavelength is approximately 0.1 nanometer. So that we need to construct a grating whose slits are less than 1 nanometer apart. So it is difficult to use a diffraction grating or to construct a diffraction grating for observing X-ray diffraction. And this solution was solved by Max von Laue and Lawrence Bragg. What did they do? Let's see. We know that X-ray is an electromagnetic wave of high energy and short wavelength. We had already discussed that its wavelength is approximately 0.1 nanometer. That means 0.01 to 10 nanometer is the range of its wavelength. From the wavelength, you can calculate its energy by the equation H is equal to h nu or hc by lambda. So you can calculate the energy of X-rays also. So, and in the electromagnetic spectrum, you can see that X-ray is lying between ultraviolet light and gamma rays. Okay, so here we are going to study about the diffraction of X-rays, and we cannot use diffraction grating as a device to observe the X-ray diffraction because the slit width should be of the same order of the wavelength of the light being used. So we have to take another method. Now, how X-rays are produced? We are using the, going to study about the diffraction of X-rays. Now, from where these X-rays are coming? So, let's study about X-rays, how X-rays are produced. And we know that in an atom, the electrons are arranged in shells like a K shell, where it can accommodate 2 electrons, in L shell where it can accommodate 8 electrons, M shell where it can accommodate 18 electrons, and so on. And think that this atom is bombarded with an electron. So what happens? The electrons will give its kinetic energy to this atom. So getting more energy, one of the electrons from the inner shell will get ejected out of the atom. I repeat, when the atom gets sufficient energy, the electrons from the inner shell, not the valence electrons, the electrons from the inner shell will get ejected out. So what happens to the inner shell? There occurs a vacancy of electron, isn't it? And this vacancy of electron is filled by the electrons in the higher shells. That means, think that from the K shell an electron is ejected out on getting energy by the bombardment of an electron. So here there is a vacancy in K shell. Now this vacancy is filled by another electron which is in the higher shells like L, M or N. Think that an electron from M shell is occupying this space. So what happens? M shell means that electron is having more energy than K shell. So it dissipates or emits its energy and come to the K is equal to come to the K shell. I repeat, when an atom gets extra energy by bombarding with an electron, the electron in the inner shell, that is equal to K shell, gets ejected out. So there is a vacancy in the K shell, and this vacancy is occupied by any of the electron in the higher shells. And the higher shells electrons are having more energy than the K shell. So whenever they get transferred to the lower energy state, the extra energy is emitted out in the form of radiations, and that radiation is known as X-rays. So let's read the slide. When the atom is bombarded with an electron, it ejects one of the electrons from the inner shell. The electrons migrate from the outer shell to the inner shell to fill the gap with the higher energy. A quantum of radiations, which is known as X-rays, is emitted corresponding to this transition, and this emitted radiation is called X-rays. So X-rays are the electromagnetic waves like visible light, and X-rays exhibit the phenomenon like interference and diffraction. But X-rays are having very short wavelength. Therefore, it is not possible to produce diffraction of X-rays by using diffraction grating. However, we can do the X-ray diffraction by making use of crystals in which atoms are uniformly spaced in planes and separated by a distance of order of 2 to 5 angstrom. Therefore, the diffraction of X-rays take place when they incident on the surface of crystals. Hence, X-rays can be used for the study of crystal structures. I think it's clear to you. We cannot use diffraction grating for observing the diffraction of X-rays. So, we are using crystals instead of diffraction grating to obtain the X-ray diffraction. And in crystals, we know that the atoms are uniformly spaced, similar to that of the uniformly spaced slits in diffraction grating. Therefore, whenever the X-rays get incident on the crystals, surface of the crystals, diffraction will take place. And the condition for diffraction to take place is lambda, that is the wavelength of the X-rays must be less than or equal to 2d, where d here, d is the distance between the planes of the atomic planes of the crystal. So thus we can use atomic crystals as diffraction grating to observe the diffraction of X-rays. And already we told that Max von Laue and Lawrence Bragg had made the solution that they used the atoms as the diffraction grating. So they consider parallel lattice planes of a crystal. See, this is the crystal having atomic planes, atoms equally spaced, so that the separation between the planes is given as d. Now here you can see an incoming X-ray A getting incident on the crystal surface and it gets reflected, and another X-ray getting incident on another atom and it also gets reflected. Now Bragg's law states that the X-rays reflected from different planes of a crystal interfere constructively when the path difference is an integral multiple of wavelength of X-rays. So these reflected X-rays interfere constructively so that maximum intensity is obtained on the screen. this is a more clear picture. Here you can see a crystal in which atoms are shown in blue color and they are equally spaced, and the spacing between planes is given as d. Here this is the incident X-ray which get incident and get reflected, and also this is another X-ray which is incident on the another atom and get reflected. So there is a path difference between these two reflected rays, isn't it? How we can find out the path difference? So this is the small angle theta. From this you can find out sine theta. Sine theta is equal to opposite side by adjacent side. From this you can find out the path difference. And we already know the condition for constructive interference, that is when n lambda or when the path difference is equivalent to the integral multiple of wavelength, constructive interference occurs. So integral multiple of wavelength is n into lambda, and it must be equivalent to the path difference. How we can find out the path difference? By taking this angle as theta. This is theta also. So this distance is d sine theta. Again also this distance is d sine theta. So what is the path difference? 2d sine theta. You can draw the angle here, this as theta. So the opposite you can find out sine theta. Sine theta is equal to opposite side by hypotenuse. That means opposite side is this distance by d. So this distance is obtained as d sine theta. This distance is also d sine theta. So what is the path difference? This is the path difference, and that path difference is 2d sine theta. So 2d sine theta is equal to an integral multiple of wavelength, that is n lambda. That is the condition for constructive interference, and that law is known as Bragg's law. So this is the Bragg's law for X-ray diffraction. And the interference pattern which is obtained on the screen is known as law pattern. Both Max von Laue and Lawrence Bragg had solved the X-ray crystal diffraction of X-rays. So the law was known as the Bragg's law, and the pattern obtained on the screen, interference pattern obtained on the screen, are called law pattern. So this is the apparatus for observing the X-ray diffraction by a crystal. Here you can see an X-ray source from which X-ray tube from which X-rays are incident on a crystal through a slit. So the crystal acts as the diffraction grating here, and from this the diffraction of X-rays occurs, and you can see the interference pattern on the screen. And here you can see the dots, isn't it? These dots forms the maximum constructive interference maximum intensity positions, and the central dot appears on the photographic plate, shows the interference maximum. So, and this pattern is known as Laue pattern, L-A-U-E, Laue pattern of X-ray diffraction. And this is the Laue method. Laue has made the experiments and he used the crystal, and he allowed the light to fall on the stationary crystal. Stationary crystal means their theta is fixed, and also d is also a constant. And the crystal diffracted the X-ray beam and produced a beautiful pattern of spots, and these spots are the interference patterns, constructive interference pattern, where you can see the maximum intensity shown by big dots. and the minimum intensity with the smaller dots. So that is the law and Bragg method of X-ray diffraction. So this X-ray diffraction also explained the wave nature of electromagnetic radiation. In the last class we had discussed about superposition and interference, and here also diffraction is also a wave property of electromagnetic radiation. Thank you.